Last time we talked about creating solids where we knew what the region on the XY plane looked like, and we were building up out of there. And so we knew when we sliced what the cross sections would look like. Today, what we're going to do is we're going to take regions in the XY plane and rotate them and see what kind of solids we get, and then ask what the volumes are. So let's just start out by drawing the region in the XY plane. So this tells us that the region's bounded by these pieces. So that part is always going to stay the same, whether we're doing area or volume. We have some region in the XY plane that we need to draw. So we've got square root of x equals 0, x equals 2 in the x-axis. So this is x equals 2. So we have this region here. Okay. And so last class, what would have happened was we would have built something out of this. So we would have had things popping out of the page from here. What we're going to do today is we're going to rotate this region about the x-axis. So I'm going to draw a little arrow indicating what axis I'm rotating this about. So we're going to take that whole region, we're going to pick it up and we're going to rotate it around. And as that region sweeps around, we're going to keep all that volume. So let me stop sharing my iPad for a second and we're going to show you what this looks like. Okay, so this looks vaguely like the square root of x, and I don't know if I have it backwards for you or not. And so what I'm going to do here is I'm going to take this and I'm going to rotate it about my x-axis. We'll think of this as my x-axis. So let's see what happens here. So this is one of those little bells that you can put on a table or hang up. So we get something like this. So this is the shape that gets traced out when the square root of x is rotated about the x-axis. So now we have to ask ourselves, how do we find the volume of something like this? And we're going to do it like we did last time, which is we're going to look at slices and find the area of each of those slices. So if you think about that, if I slice this shape and look at what that cross section looks like, it's going to look like the end of this, which is circular, plus or minus some little indentations from the fact that this is a little party paper. So we should be getting circles if we slice. You could also think about this by drawing a line on here. So let me do that. Draw a line on your region. And then, whoopsie. So there's my line. So think about if I rotate that line about the x-axis and come back to where I started, what shape am I going to get? So you're not really going to be able to see how that rotates all the way around, but you should hopefully notice that that will trace out a circle. So the cross sections are circles here. And so what that means is in order to find the volume of this region, I need to find the area of one of these little circles and then integrate, because that's exactly what we did last time. We said to find volume, we integrate area. Okay, let me give you one more visualization of this before we actually do that, because this is a nice little visualization. Okay, so what they have here is this is the x-axis is the red one, the y-axis is the green one. So we've got our xy plane just tilted a little bit so that we're going to be able to see the motion here. Okay, and then that blue curve is my square root of x going up to 2. So what I'm going to do is I'm going to take that region and rotate it around. And so you see that we're creating a solid. And you see they've drawn these little cross sections. We're seeing that circular shape as one of the cross sections. So this is hopefully very similar to what I was showing you before. So our goal is to find the volume of this region. And in order to do that, we're going to find the area of our cross section and then integrate. Okay, so we're going to need to know what the area of one of these little circles is. And if we think about that, to find the area of a circle, I do pi r squared. So the thing that I need to know is what is the radius of that circle? And if we look at this, the radius looks like it is dependent on that function square root of x. If I move that little circle, if we get a bunch of circles here, if I move that circle along, the radius of the circle is going out to that function square root of x. So no matter which x value I'm at, the radius is square root of x. So that's exactly what we're going to do. So let me bring my iPad back up here. This is going to be called the disk method because we have a little disk that we're working with. So let's do this. So I'm going to draw my little line segment on here. So this is my little line segment that I'm rotating about the x-axis. When I rotate that little line segment about the x-axis, I get a circle. Okay. The length of the radius here is square root of x because that's just the length of this line. It goes from square root of x to 0. So that's the radius, square root of x. So the area of one of these circles is pi r squared. So that's pi root x squared. So to get volume, just like we did last time, we're going to integrate our area function. So we're going to integrate pi. I usually pull the pi outside, square root of x squared, which you could definitely write as an x. My bounds are going to be based on that yellow region, are going to go from 0 to 2, since we're working in terms of x here. Okay. Notice that if we tried to do things in terms of y in this case, we would have line segments going this direction. If I rotate that line segment about the x-axis, I'm going to get something that's not just a circle. It's going to be like the shell of a cylinder. So this method would not work if we were doing things in terms of y for this particular problem. Okay, so this thing that we created here is called a solid of revolution, and we're going to talk about finding volumes of solids of revolution over the next couple of class periods. Okay, so let's just jump into another example here. So this example, we're taking this region, square root of 4 minus x squared. That's the top half of a circle. You can draw that in Desmos if you don't believe me. So this is my region. And we are rotating this guy about the x-axis again. Okay. So if I rotate this about the x-axis, let's see, my numbers go from -2 to 2 by looking at the graph of this function. Okay, so in order to get a circle, when I rotate this, I need to use a little line segment that is perpendicular to the x-axis. The length of that line segment will just be the function, just square root of 4 minus x squared. So I'm going to integrate pi r squared. So square root of 4 minus x squared squared dx. My bounds are going to go from -2 to 2. Okay, so that's going to be the volume of this region. This particular region, let's see if we can look at this here. So we've got, well, let's do it this way. So we've got our semicircle that we're rotating. This is that little line segment that I'm thinking about. We're asking what is going to happen when I rotate that guy. So when I rotate this whole thing about the x-axis, maybe, there we go. We're getting a shape like this. This looks an awful lot like a sphere. This should indeed be a sphere, because if you think about taking a semicircle and rotating it about the x-axis, you should get a whole sphere. And so if you think about slicing the sphere along there, you're going to get a bunch of circles. And so that's why we're finding the area of a circle. Okay. So both of these regions that we just did were kind of interesting because they touched the x-axis. The bottom of the region was all the way up against the x-axis. We can also look at examples where our region does not totally touch the x-axis, and that's okay. So let's do another example here. So this one has the square root of x and y equals x. Okay, so these two intersect at the point 1, 1. We're rotating this about the x-axis again. Okay, so we've got this little region in here. Okay, so we notice that this region no longer totally touches the x-axis. And so when I rotate this, I'm not going to have circles when I slice because there's going to be kind of a gap in the middle. So we need to think about what's happening. So again, I'm going to do my slicing perpendicular to the line I'm rotating about. And so I want to ask myself, what do I get when I rotate that little black line segment about the x-axis? And you might believe me that we're going to get like a little washer here where the yellow part's that. If you don't believe me, let me try and show you how this would work with another demo here. So this will pull up in just a second. Maybe. There we go. Okay, so this region again is the region that we were just looking at. The blue graph is square root of x. The red graph is y equals x. And we're going to rotate this about the x-axis. And so you notice as I'm rotating this that there's kind of a gap in the middle. And so you should ask yourself, what is that little cross section going to be? Well, that little cross section should be a disk. And again, I'm going to have a really hard time. There we go. There's that little cross section as a disk. So now what we need to find is find the area of, we really call this a washer, not a disk, sorry, because it's like a washer that with like nuts and bolts. So we need to find the area of one of those washers, and then we're going to integrate. So the way that we find the area of one of those washers is we need to know what the two radii are, because we have two different circles, and then we're going to subtract those. So let's do that. So here's the formula down here, and we can usually pull the pi out. So we're going to have an outer radius and an inner radius. The outer radius is this one, and the inner radius is this one. And so if we think about that, what that looks like on our graph, we start at the line that we're rotating about, and then we go up to some curve. That's going to be my inner radius. That's not how you spell radius, but you can fix that. And then if I start at the line I'm rotating about, again, the x-axis here, and go up to the second function that I hit, in this case, the square root of x, that's my outer radius. Okay, that's the radius of the big circle. The inner radius is the radius of the smaller circle. So to find the volume in this case, I'm going to integrate pi. I'm going to integrate from 0 to 1 because that's the bounds on the yellow region still. Okay. And then I need the outer radius squared. The outer radius is the length of that black line. That black line goes between the square root of x and 0. Y equals 0. And so that's my outer radius squared. My inner radius is the length of that red line. That red line goes from x to the x-axis, so x minus 0. So we get something like this. So what we're doing is, again, we're integrating an area in order to get volume. Okay. I'm sorry that this video is fairly long, but these are a lot of good examples. So let's do a couple examples where we're going to rotate about the y-axis just to get some practice here. So let's see. So we've got x cubed. That's y equals x cubed. Y equals 8. And then the y-axis. So we're looking at this region here. We're rotating this about the y-axis now. So in order to get circles out, I need to rotate a line segment that is perpendicular to the line I'm rotating about. So I'm going to have a little horizontal line segment here, which means that my integral is going to need to be in terms of y. Okay. I notice if I rotate that little black line segment, I'm going to get a complete circle out. And so I am just going to need to integrate the area of that circle. So the length of that line segment will be the radius. I need it in terms of y. So x is the cube root of y. So that's really just going to be my radius here, the cube root of y squared. We notice that we don't have an inner radius, or our inner radius here would be 0 because there's no gap in the middle. Okay. My bounds will be 0 to 8 because those are the y values on this region. Okay. And one more here before I stop recording. Okay, so we've got y squared, or y equals x squared. Y equals 2x. Okay, and this is rotated about the y-axis again. So again, because we're rotating about the y-axis, in order to get something circular out, I need to rotate a line segment that is horizontal. So my integral is going to be in terms of y here. This point here is the point 2, 4. So my y values will go from 0 to 4. We notice that we're going to have a gap in the middle here. So we're going to need an outer radius squared minus an inner radius squared. I'm going to put my pi on the outside so I don't forget it. We're going to have things in terms of y. So let's solve these. So this blue line is x is equal to y over 2. The black line is square root of y is x. Okay, so to find my inner and outer radius, I start at the line I'm rotating about, the y-axis. I go to the first thing I hit. That's going to be my inner radius. So my inner radius is the distance between that blue line and the y-axis. So the blue line is y over 2. The y-axis is 0. You don't have to write the 0, but it's good practice for what we'll do later. Okay, and then my outer radius, I start at the line that I'm rotating about, the y-axis, and I go to the second function I hit, which is square root of y. So the length of that line segment, we're doing right minus left every time we look at length, or top minus bottom. So right minus left here. The right function is the black one, square root of y. The left function is the y-axis. So we get something like this. And we'll do lots more practice in class.